So section 6.4, we're going to be pumping water out of different shaped tanks. And one thing that they'll tell you about water is its density. Typically speaking, we're going to work in English units. Now, I didn't really want to mess around with the font on this, but rho, the Greek letter for rho, kind of looks like a P. Looks more like a P than it does an R, but it's basically their Greek letter R. So its rho is 62.5. You'll probably have that memorized by the time you do all the problems in the homework, but that's pounds per cubic foot. That's the density of water. I want to figure out how much work that is to move that out of a tank. Now, a little bit of physics that I'll remind you of, and that is work is going to be, well, maybe you guys know it. What's the formula for work? Work is force times distance. Okay, great. Force times distance. Let's figure out what the force is going to be required to move some of these objects. So we're going to look at this figure here, and they give us some dimensions. They tell us that A is 3, B is 4, and C is 6. And what we're going to try and do is figure out how much work is done moving that, some of the water out of this. Now, this is going to take a page out of our book from our work with volumes by shells, volumes by disc and washer, in as much as we're going to take a little slice here, a slice of this region, and try and figure out what the mass of that one slice is. That'll be the force. So our force is going to be the density of this times the volume. And if you notice, I'm going back to kind of real fundamental stuff here, because these aren't formulas that I care to remember. This is just stuff that I want to be able to work out for myself as I go through it. Now let's take a look at our slice. I want to find the volume of one slice. One slice. If I take a horizontal slice through this, then what kind of figure does that look like? What figure am I going to get when I take a horizontal slice through that? What's it going to look like, more or less? Yeah, it's going to be a rectangle. And the volume formula for a rectangle is going to be, volume is going to be the length times the width times the height. Now, in doing these problems, one of the things you're going to have to set up for yourself is a little coordinate system. I'm going to make this coordinate 0, 0. That's the origin. And in fact, what might make it a little bit easier for me to see and relate to is if I just look at this in profile and not worry about, the 3D aspect of it. We're going to pump it out off the top edge. So let's just draw ourselves a little figure here. All right. So that's our figure in profile. We've got a height of 3 and a width of 6 here. This, of course, is 0, 0 at the origin. How about the coordinates here? What are the coordinates there going to be? What are the coordinates of that point going to be? Yes, 6 and 3. 6 is your x distance right there, and then 3 is your height, so 6 and 3. And we're taking this slice through your region. what's the thickness of my slice here? Somebody said it. dy. Thank you. It's going to be a dy slice. That's going to be the height of our slice. But unfortunately for you, there's some more work that you're going to have to do for a problem like this. And that is, you're going to have to figure out, well, you know, what's the length and what's the width. If you put up figures like x and y here, then maybe that'll help us out a little bit. If that's x and y, then when we come over here, that's going to be 0 and y, right on the y-axis. Now, if our height is dy, then we're going to want to do everything else in terms of the variable y. What that's going to mean for us is you're going to need an equation for this line. You need an expression for that line. Now, I'll give you a little bit of a hint. It has to be y equals mx, right? Why does it have to be y equals mx and not y equals mx plus b? What is b in this formula? Remember? What's the b represent? Yeah, it's the which intercept? The y-intercept. What's the y-intercept? Yeah, so the y-intercept is 0. So we have some formula y equals mx. Good. Help me remember what the m is all about. Slope of the line. What's the slope of this line? Not 2. Yeah. So slope is rise over run. The run is 6. The rise is 3, so you get a slope of 1/2. So we get y equals 1/2 times x. Great. That's one thing you really, really need for a problem like this, is that equation. Well, let's keep in mind, what we really need to do is we need to find the width and the length here. Now the length is going to be this dimension that I'm not really trying to represent. That's just going to be 4. So that's not going to change. But the width is going to depend on the height. So let's see how it depends on that height. Your width is going to be what in the last section we called our radius. That's going to be this distance, x minus 0. Width is x minus 0. But if you solve for x, what do you get x equals in this case? Awesome, thank you. 2y. So 2y. All right. So we've got a couple things here now. We've got the width, we've got the height, the length. This length is just 4 throughout the whole problem. So you don't have to worry about changing the length at all. The length is just 4 throughout the problem. So we've got a couple parts of what we need here. The length is 4. The width is 2y. Our height is dy. So overall, we can find the force on one slice. So let's do that. So the force on one slice, force for one slice is going to be the density times L times W times HT. I'm going to leave the density out here for just a second. So it's going to be 4 times 2y times the height, which is dy. Or in other words, 8 times rho times y dy. Sorry about that. Didn't realize I was underneath the viewing screen. So that's the force to move one slice. Okay, great. Now, the work done is force times the distance. How far do we have to move that slice? So let's keep in mind that we're going to be pumping out that water at the top edge. So the distance that you're going to move that one slice is really going to mean finding how far between your slice and this top edge. Now that top edge has a height of 3. So the distance that you're going to move that top edge, or to move your slice, is going to be top minus bottom. Let me draw it here so I can try and make sure you're seeing what we're doing here. All right, so let's put back in our slice. This is some point, say, x and y. What's the equation of this line? It'd be y equals 3. We want to figure out the distance that you're moving that slice. So what is that magical distance? How far are you moving that slice? Or what's the distance between here and here? Somebody said it? 3 minus y. Distance equals 3 minus y. So now we're going to put all these things together. The work done in moving that one slice of water is going to be the distance times the force. So work in moving one slice work equals force times distance, and we have expressions for both of these. The first one is going to be 8 times rho times y times dy. The second one is going to be 3 minus y. Now, if we recall that the density is 62.5, I think that means 8 times 62.5 would be what, 500? Somebody check me on that. So, thank you. 500 times y times 3 minus y dy. That's the work done in moving one slice. Right there. So a lot of setup to get here. Let's set up the integrand and we'll finish it with fn int. As far as the integrand is concerned, we have to add up not just the work of moving this one slice, we want to add up the work of moving all such slices. So what do you think is going to do that for us? That we're going to add up the work of adding or moving all such slices to the top to pump it out. What's that last step I need to do to get my answer here? Integral. Integral, we'll take the 500 out in front. Y times 3 minus y dy. Good. Someone else finish it up for me. What are my limits of integration here?
0 to 3.
Yeah, 0 to 3. So keep in mind, this is the point 0, 0. This is the point 0, 3. These slices can be taken anywhere in this region. So 0 to 3. This is a polynomial. Finish it up with fn int. I'm not really interested in you doing the rest of these kinds of problems. I mean, doing polynomial integration with something, well, exactly by hand. So let me get rid of this. Math 9, 0 to 3. And I'll just distribute the y there and write it as terms in x's, 3x minus x squared dx times 500 is 2250. Now there's one last thing here. Work is done in terms of the English system of measurements, which we're using here, regrettably. That's going to be in feet times the force, or foot-pounds. So foot-pounds for your final answer. Please include those units. Comments on this last one here? Don't worry, I only put 8 or 9 of these on an exam, so it should be in good shape. Gina's going, oh God. All right. All set here. We'll do some more on Thursday.